Yeah, for sure. And I actually want to take that you've been outside. Yeah, yeah. So, good morning, everybody. Good morning, everybody. Thank you for attending to this presentation. It's a pleasure to me to introduce Professor Pavel Neushi. I met him some years ago in the University of Brno. And just let me tell you something about the track of Pavel. He has a very long track record in research. He did his PhD in Prague, in Czech Republic, in the Technical University of Brno, in the Czech Technical University in Prague. He later was working in the University of Illinois, Stanford University in US, also in Singapore in the Institute of Microelectronics, and then later in the Institute of Bioengineering. Nowadays, he's working in the Northwestern Polytechnical Institute in Xi'an, in China. He's also part researcher in Brno University of Technology. And he will tell us today his story about the journey of the miniaturized systems for real-time PCR. So I hope you enjoy the talk. And thank you, Pavel.
Thank you, Steph, for the introduction and for inviting me here. I'm very happy to be here with you today. So, as Stella said, I did quite a few things before. And a part of calorimetry, bolometers, ISFETs I did before, and MEMS. Currently, today I will talk about one specific part, which is systems for nucleic acid-based diagnostics. And so we do low tech. Here is very brief contents of my talk, and whoever works in microfluidics for longer time, thank you. You know that here. 15, 20 years ago, practically every talk of microfluidics started with this picture. And showing that like a wonderful small chip will replace entire lab. And you know, basically by now there was basically naive imagination. And when I met my former boss, his name is Andreas Mans. He can be considered as somebody, not inventor, but better to say somebody who triggered interest in MEMS, which I think he did. When I met him first time, I told him, "Hey, Andreas, you didn't create it lab on a chip." He said, "Why not?" He was very upset because it was his like buzzword, his like baby. I said, "You created chip in a lab." And he said, "What do you mean?" And he was very upset when I said it. I said, "Yeah, look at it, and nothing wrong with your device. But you have 1 square centimeter chip, and half of the room fills equipment. Where is the lab on a chip? This is chip in a lab." And I'm not laughing at him at all, and I was laughing at him either, because 20 years ago, for laser-induced fluorescence or fluorescence, basically you have 2 options: mercury lamp with filters and 20 kilogram water-cooled, I think this is argon or nitrogen. I think argon laser. And that's it. So why don't you use blue LED on? It doesn't exist. So you can use something that doesn't exist. Now we have that. We have cheap sources, which he didn't have before. So he really have like a huge piece of equipment to detect small chip. But anyway, this is what he showed the past. Okay, a few examples here. This is, I believe, from Chip Shop from Holger Becker from Dresden. This one is Veritas Laboratories from Singapore. This is endpoint detection PCR with multiplexing. This is some signal analysis chip. I think Fluidigm, I'm not sure. And this is on Agilent. So also I like to say one thing, that when we say microfluidics, we always in this community we always mean biomicrofluidics. But sorry, microfluidics is here much longer. Inkjet printer is microfluidic device, and if you look at the volume of many of those chips and our chips, we are basically nowhere, because they have like millions and millions of those chips. We have few. A few thousand, let's say. And again, I don't know, I think it sounds funny, but And also coffee makers, I believe they use microfluidics now. So from this point of view, yeah, we don't, I don't like to talk about those microfluidics because compared to them, we look like total losers, okay? But anyway, so we came with, it was during time when there was avian flu and SARS. I was then in Singapore. So we wanted to create handheld small systems which can compete with big boys like here ABI, qPCR. And you know it, basically you need to take sample, you dump it into lysis buffer. And you might remember during PCR testing of COVID-19, there was like pink color liquid. And this pink color liquid has very important function. It will lyse or break cover or shell of the virus. And two outcoming results. One, both are important. Ones, it will release RNA, but especially second issue, which is very important, it will inactivate the virus because the moment it breaks the shell, virus is not virus anymore, and it cannot contaminate anybody, cannot affect anybody. So that's why the moment you dump it there and the lysis buffer starts working, it's kind of safe to work with it. Okay, so we should keep gloves and so on, but it's much safer than without it. So this very important step is here. This is this lysis buffer because it will break the virus and make it safe for people. So, sorry. So we came with the idea of over 20 years ago to make a device which will be like small. This is roughly palm size, what you see here. And there's also funny story with this. We submitted to, I think, LOC one time, level on a chip journal, and that reviewer was very upset and saying, why do we call obviously computer generated picture as photograph? So I sent him back, can you please explain me why should I call photograph computer generated picture? Because this is photograph. And we play with, because I was one while back, 30 years ago, I was thinking I might be a professional photographer, or at least partially. So you will see, we do have pictures which are generally quite nicely done, because if not, we don't publish it because we would feel like ashamed of it. Okay? So, but this is a photograph. Anyway, so we decided following features have to be fulfilled. First one, you are here from, many of you have chip fabrication background, so you know one thing, you can have a silicon chip contaminated with RNA, DNA, you dump it to Piranha solution, absolutely no way any DNA or RNA will survive. This I don't believe, and this can happen. Problem is, your customers are doctors, they don't believe you. And they don't care. They want disposable anyway. You can tell them zillion times, you can prove it, nothing survives. You say, yeah, interesting, but I want disposable. Okay, fine. So we decided it has to be disposable. Has to be efficient, comparison is normal, but the operator is also funny part. These are different, but we talk about beginning of this century, and we plan with this naive idea, we go for like rural area of Africa or Southeast Asia and so on. And that's why told me just plug it to USB. I said, then I also want one picture from village in Africa. I'm not sure how old this is, but maybe not that old. And funny part was, it was really very rural place. The only power source they had was 12-volt battery of the car. And during daytime, they use the car. In the evening, they stopped working. They connected TV to the 12 volts, and they were watching TV at whole village. So I told them, like, what USB? Like, or what 230 volts AC? Or 210 volts in US. And some places they don't have it. But we decided that the battery 12 volt is everywhere because cars are practically everywhere. Okay? And this is now outdated because in beginning of the century, sometimes RT-PCR, reverse transcription PCR, was not that stable. Chemistry was not as good as today. So very often this reverse transcription failed. But I put it here. But these days, chemistry is much better. You buy the kit, so this is automatic. So we came with this system shown here. It's micro machine silicon. Here is quite naively shown as a line of gold two lines. One is heater, one is sensor. So we can, with closed feedback loop system, we can control temperature of the silicon. Silicon thermoconductivity lambda is 170. So temperature here is practically identical as temperature here. This is normal 500 micrometer wafer. And this is the key part. This glass is placed on the silicon chip, and there is little layer of oil which is sucked inside by capillary forces, transferring heat from here to here and through the glass to sample covered with oil. We call it virtual reaction chamber. And this part is disposable, the glass. Silicon is not. And silicon does have to be disposable because there is no contamination of silicon material by the sample, because sample is on the glass. Here's photograph again, how the original chip look like. This is 24 by 24 millimeters, so not very good for 4-inch wafers because you get only 9 chips per wafer. But and this is not sample, this is blue ink to just increase contrast. And again, as I said before, this is photograph including this part. Took me 2 hours to position the lights to get those stars coming into the camera. So this is not Photoshop, this is photograph. And heating is done by the available power. So if you lower resistance or increase voltage, you get more power, of course. Cooling, this is passive cooling. Passive cooling done by time constant of this. Basically, how quickly this heat can disappear with through this bar outside. And you can see some numbers here. Micro is this I just showed. I have also smaller one. So heating is 50 Kelvin per second, cooling is -30. Smaller one is significantly faster. So actually, this cooling is pretty good. In 2006 or 7 was considered one of the fastest PCI in the world because of this number here. But this is PCR. PCR, when you finish it, you need to somehow detect the product. So we normally use only real-time PCR, quantitative PCR. And the reason why we do it that way is not because we would like to know the quantitative information so much. For instance, for COVID-19, SARS-CoV-2, you don't care, at least in China, you don't care what is critical threshold. As long as there is some critical threshold, you are sick, go to quarantine. Very simple. So we are not interested in this part, but we are interested in something else. When quantitative PCR, you don't manipulate sample for detection. You detect during PCR, you detect the product, and when PCR is finished, you are finished. So there is no need to pipette anything somewhere else or move somewhere else somehow or whatever. So that's why we use real time quantitative. And beginning again, this is like 2003, 2004 year. What we did, we did big investment. We bought for $7. We bought DVD mechanics. Open it, look inside, and like reverse engineering, you know this, what that means in real life. So we got inspired same way here, and we basically copied the system and simplified because we don't need to move anything. There is some flying hair, we don't need that thing. But if you look inside DVD head, optical head is practically identical. Light source, some beam splitter, lens for focusing on the sample, and going another filter set, another end to the detector. So we have here. Except this one is blue LED, the use red laser. This is blue filter, diachronic mirror, as the FITC system. Filter set, so means for people who are not familiar with the service system too much, I call it blue in, green out. And here inside is after this detector, there is photodiode. We tried to use Hamamatsu a while back because $100 per piece didn't work very well. We use BPW21 from Siemens, which is generic photodiode, and somehow I don't know why it worked much better and much cheaper, of course. And here is amplifier inside. So this is made of metal and with little cover here. So it's closed, and this light coming from here is modulated. And we use lock-in amplifier, which is built in the system to process signal from here to avoid, to eliminate like this light influence. This is 50 Hertz. Sunlight is 0, is DC. And we use 1-point-something kilohertz signal for modulation here for the LED to make sure that these all lights are eliminated. So we have three systems. first generation, second, third. So it was quite failure, I have to say, because its modular system can do many things, which means it doesn't do anything very well. Okay, so but it could do like electrochemistry, it could do like PCR, stationary PCR, which can move, and many other things, nanovirus testing. But we then move here, and we decided that what we want is simple system which has one function and nothing else. Okay, not changing like here. I can change the top to the LSPR by the configuration. I can change a head to another head, another head, another head. And as I said, two things, too complicated, too many things together, and real life, not very good. So this one might better. Some results we have done on the generation one. This is avian flu RNA. This is, and we do something which I do quite often. It's called continuous fluorescence monitoring. So instead of getting like 1 point here, as normal PCR will provide you this curve, and then melting curve analysis for like cybergreen, we collect many samples, and then we process them by typically by MATLAB or inside by some processing to get this curve out, which is shown here. So we have, and I will get that later a little bit, because we also use some information from the data which normally are not available in PCR for users. So this is single color first generation. First generation was not very successful. It did work somehow, but there's problem that this silicon chip is soldered directly to main PCB, and if you break the chip, you have to basically replace the entire PCB, which is pain on neck. This is, I believe, this might be Ebola RNA detected, and we have 4 samples. 4 samples we decide minimum, because one is negative control, one is positive control, and 2 are actual samples. And for people who are familiar with it, it's very simple, certain way. Just imagine you are a doctor, and you have patient who might have HIV, or maybe not might have, but who you think is option or chance the person might have it. If you messed up the PCR test, and which means, for instance, is not correctly mixed, so you get no amplification, and you inform the patient who actually is HIV positive that hey, you don't have HIV, and that implication, of course, because it's called false negative. Or you have contaminated sample, you get amplification, you inform patient who does not have HIV, you have HIV. And again, from social aspect, there are big implications. That's why two samples must be there. One is called negative control. You don't put sample into it, you put there water instead of sample. And positive control, you put RNA of that virus you are looking for. And the positive must be positive, negative must be negative. If negative is negative, means no contamination of your lab. If positive means you mix chemicals correctly, and so you can test those results. Very important. So 4 is minimum. These are Ebola virus tests. That's not interesting. Go quickly. So we also detected the second avian flu. Is it? And I moved to China, and we decided to somehow revive the project. And we created version 2. And you can see one difference here. The PCB, this chip, has connector now. So if a student pushes with his finger, which happens quite often, unfortunately, when they start with it, they will break the silicon micro machine chip, and we need to replace it. So what we do, we unplug it and plug it back, plug it out the back. So, and this is made by CNC. You can see it here. This blue LED, blue filter, diachronic mirror, focusing lens goes up. The sample, which is here, goes down through the diachronic mirror, green filter, photo detector, amplifiers. It can be controlled from either PC via USB. We can control also it from via Bluetooth from cell phone. And I have it here. This is actually a very funny picture certain way. This is map of Xi'an. Yeah, it's quite old city, but and this is city walls, and just who does not know China never does anything in small scale, okay? Because small scale is not interesting. So this city wall, which is complete, is 14 kilometers long. Okay, just imagine. Okay, about and means this is about 12 meters high and 10 meters wide. So it's not nothing small. Okay. Anyway, but there is a hospital, and we propose this is a mock-up picture. We didn't do this testing. And it's written in the paper, this is like proposed or mock-up picture, how it would look like. Just imagine you have the device, I feel sick, so person goes there, test that potentially sick person on spot, and gets on cell phone the curves. You have amplification curve PCR and multi-curve analysis, and automatically with GPS coordinates sent to the center via some application. I have one person sick here, I have 15 person sick here. It was the idea, and I have to say one thing. It showed COVID-19, at least in China, shows me how naive it was, because China's system was done different than here. Together with actually New Zealand and Australia, they had something different. They call it zero tolerance policy. Australia and New Zealand ended earlier, China ended later, and means they didn't want to have any virus inside. And when there was this Omicron, I forgot what was the version. After Delta was the next one. It's very contagious. And the time was spreading in China. It was in October, a year ago and something. And Chinese government decided every person in China has to be tested every other day. China has 1.4 billion people. Every other day means you have to test 700 million people every day. And what they have done, they did so-called pooling. And who is not familiar with it? When you do flat screening of entire population of something which you know is not if every other person is infected, it's first story. But if very few people are infected, you want to test many people. What do? You combine samples together from 20 people in this case, and test them as one sample. The sample is negative, means 20 people were negative, and you don't have to deal with them anymore, because you with one test you get 20 people tested. So they did 20 to 1 for one, which means I think 35 million tests per day. And with every city with population above certain limit, there are collection centers, and it was somehow ruled that nobody should walk more than 5 or 8 minutes or something like this from home to get to the center. So, and if you want to go for a test, yeah, it costs 0.4 euro per test. No, 0.4 euro. Yeah, about 0.4 euro. Each test costs you about 0.4 euro. The PCR test, okay, I'm talking about. It was also funny. Europe were buying big time antigen tests, which nobody uses in China. So they don't use here. They use all of these only RT-PCR. Anyway, so certainly realize, and it's not like I'm advocating China here, not at all, but I saw how the system can be done, which basically totally eliminated need of this. Because like, why do you need it? You don't have to get like somebody coming from here to here to take your sample. You go from here to here, there's collection center, give them your sample and go home. So they were able to do it quite interesting way, and I start doubting how important is our device. I still like it, but I'm not sure how important it is anymore. Okay. So then we move to dual color, single color, FITC only. Also dual color, which is slightly bigger. What is bigger only here? This is extended because there is optical system, which is bigger. Here's cross section of the system, and it can detect 2 genes at a time, or 2 colors at a time, 2 channels at a time. One is FITC, one is Texas Red. In order to detect 2 at a time, I need a filter cell, which is dual bandpass filter. So there has to be certain gap, because in between this gap, I have to get this the emission spectra, and which means I cannot just select whatever I want. I can select FITC and Texas Z because they do exist. Something with longer wavelength than Texas Z might be also used, but you cannot use, for instance, FITC and GERL because GERL is just here and there's conflict between light coming in, light coming out, so you cannot use it. But two are okay. So we have this first filter, two merging optical paths of blue and yellow LED. Dual bandpass filter, this one is here. Dual bandpass recurrent mirror, which is this one. Bounces off to the sample, go down, get through this, and this is detection filter, which is shown here. So, there are four photodetectors, and I forgot to mention one thing. In electronics, we basically get signal from all four photodiodes together as one signal after basic amplification. And which means we have only one lock-in amplifier, and how do we find out which one is which? Very simple, because we have only one LED activity at a time. So we get actually 8 pulses of signal from these four photodetectors, and we know which one is which because the controller which does it knows it because it also controls the LED. Okay, so it's shown here. And yeah, the basic schematic is shown here. Nothing special, basically. You have MOSFET controlled LEDs. There is we use last time Brown optical instruments, OPA 129 because very low noise system, and it goes to lock-in amplifier and goes to processing and to display. And we also use temperature control here, which is same thing as before. I said before, it's closed feedback loop system for with PID to control temperature. And we can communicate with it from USB via USB, or we can also communicate with it from a phone. Typically, we use USB because more convenient on the laptop or PC to type the numbers. So we need to define protocol. So it's much easier to type it on PC than on phone. So we prefer PC here. And you can activate either FIPC or Texas one. Plus PID. Some results which shows that two genes from SARS-CoV-2 virus, and this one also using SARS using this pro-based, this single channel FITC using EVA green and melting analysis to show that the temperature is specific to the we are looking for. We also did LAMP. There's some discussion before. LAMP is I keep forgetting loop amplification mediated something, and simplified we can say is isothermal amplification of nucleic acids, specific amplification of nucleic acids. There is a lot of buzz about it these days, last few years, like how much better is than PCR. Yeah, we do it because sorry, for practical reason, we cannot get funding for PCR anymore. We can get funding for this marvelous technique LAMP, which is much better than PCR, but we don't believe it because PCR is much better. But we have to create a story. Okay, sorry. You know how it goes. Okay, so it will towards all electrochemists, but if you have biosensing with electrochemistry, you claim how much better than fluorescence. It's just joke, okay? But you have to write it and to serve. I am electrochemistry a lot, okay? So then you don't wait. But if I have to choose for practical application fluorescence or electrochemistry, I would never touch electrochemistry because fluorescence is so much better. But when we do electrochemistry, we explain how electrochemistry is so much better than fluorescence, okay? Even it's actually opposite. LAMP is the same. LAMP has quite a lot of headache. For PCR, you need 2 specific primers to the target you are looking for. LAMP requires 6. But there is advanced, and LAMP practically cannot give you multiplexing. It's almost impossible. In one well, detect 2 genes using LAMP. It's you will have 12 primers that will start colliding with each other, primer-dimer reaction, and you get nothing. So it's not that good. and also slower than PCR. Even people say yeah, much faster than PCR, but they compare microchip lamp with big old PCR system. Here you see how we are faster, but so they ignore that also small fast PCR. And fastest PCR ever was done by Carl Whitwer, which was 0.6 second per cycle. But one has to be a little bit cautious about that number. And the reason is, yeah, it did work, but he used such high concentration of DNA which doesn't exist. Okay, so yeah, he shows that it can be so fast, but for any practical sample, I showed it to my coworker from Charles University in Prague who does PCR. He was laughing at me. I said, "What is this joke?" She asked me. So what do you mean? Very fast PCR. But she said the DNA is about 100 to 1,000 times concentrated than normal concentrated sample. So it doesn't matter too much. You can do PCR in cycle 5 seconds to 10 seconds, much faster than LAMP. Okay. And another thing is where LAMP is good, LAMP changes pH with reaction. So when you get amplification of DNA or RNA, because you can do RT together with LAMP, you get change of pH, which means if you put pH indicator into the solution, which we do, color will change. So this is beautiful. This is a good part because you just look at it and you see positive or negative just by looking at it. Okay, PCR cannot do it. Okay? And one more thing, because there is no cooling, you can have thermally insulated system and very low power, which is true. For lamp is better from this point of view. I'm not sure I'm much interested in this part, maybe I can skip it. We did some cyclical multiplexing, quite a few, and maybe it's not interesting here. Now, oh yeah, we also do digital PCR, and digital PCR is basically endpoint detection PCR. And why it's called digital? Well, very simple, because sample is digitized. What does it mean? That converted into binary number. And here there's no number. You split sample into subsamples, we call partitions, and let's say you have typically more partitions than DNA molecules. And say you can ignore now Poisson distribution, and if you ignore it, so you can get either 1 or 0 sample in each partition. It's called digitizing, for digital PCR. And then in this case, we have 26,448 partitions. And you can see here on this picture, there are some green, some are not green. And very simple. I forgot to mention, but when you do PCR, you're basically multiplying the number of DNA sequence of your interest. And you have 40 cycle, each cycle multiply by 2. So theoretically, you could have 2 to the power of 40 number, and 2 to the power of 10 is 1,000, 2 to the power of 20 is 1 million roughly, there is 1 billion, there is 1,000 billions. So you can get 1,000 billions of samples times original number of copies. And if original number of copies is 0, your result is 0. So that's why you have some of them green, which means some DNA was there, some of them are not green, DNA was not there. With digital PCR. And advantage of the system is you can get quantitative information. You can find out how many copies you had in the beginning. And when you ask question, when do you need it to know? It's a very funny question, because very rarely. But there are cases where you absolutely need it. And what we do, for instance, it's for prenatal diagnostics, when you are detecting from mother's blood if the fetus might have some genetically born disease like Down syndrome. At that moment, again, you don't care how many chromosome 18 is there, but you need to know ratio between chromosome 18 and chromosome 21. And if you have more chromosome 21 than 18, you get trisomy 21, which is Down syndrome. If you have opposite, more 18 than 21, it's called, I think, Edwards syndrome. Edwards syndrome is not that well known for one reason, that child with Edwards syndrome typically doesn't survive first year. So people cannot see like adult people with Edwards syndrome because they don't they don't live over 1 year. But Down syndrome, I guess you know what it is, and basically makes some big burden on the family. So what is now as a standard in the Czech Republic, there is testing of the mothers in first trimester. And if they find out with non-invasive technique, because this is from mother's blood, that there is high chance of Down syndrome, they can go for more invasive technique, which can actually cause about 1% causes miscarriage. But the moment you know already from the previous test, which was non-invasive, yes, there is really potential high chance of this. It makes sense to go for it, and then it's up to, and they find out it's yes positive. The fetus does have Down syndrome. Is up to the mother to decide what to do next, because nobody will force her to go for abortion, but it's her choice what she will. But she, by our regulations, she needs to know it. Okay, so the PCR. So we have a project. We developed this handheld system based on P4 Huawei phone. Details are shown here, and so this is where the chip is. Underneath the Peltier element or PVC cooler for heating and cooling, plus cooler here, which is cooled by fan to remove excessive heat from here. Otherwise, we've got thermal runaway and it will overheat everything. So when I take the phone out, you see this. So there's optical system, again, FITC, blue LED, same thing as before. Blue LED, blue filter, dichronic mirror, shine on the chip, go green light goes up, passes this filter, green filter, and captured by image by a camera of the phone. And originally we wanted to process it in using cloud MATLAB, but we found that the functions we need to use in cloud MATLAB are not available because there's some toolbox we needed, so we use it offline. So we send it by application to the PC, process and send it back and get the image on the screen. That's all the detail of this device. Where is it here? This is some outputs. Normally, people who do DPCR, they like these graphs. I don't. I prefer these ones, so we always show both. So, and here we just have multiplexing, I think. Yeah, 2 targets from SARS-CoV-2 genome ENN. One was we use technique. I'll talk about it now. I think I have it here somewhere. For multiplexing on single color, because it's a single color system. So yeah, we put here FemProbe target 2. So target and in environment of EVA green. So target 1 was shining, producing fluorescent due to EVA green presence. Target 2 due to EVA green and FemProbe presence, which means this amplitude was higher than this one. That's why it shifted up here. Okay, so I separated from target 1. If we don't use the FemProbe here, these 2 peaks will be next to each other and overlapping each other. Now we add more, let's say, fluorescence here, so we shifted up to this. Okay, we use it for multiplexing as well. Yeah, this is how it looks like. Some details, a picture. There's some defect which we eliminated. We have protocol, which is quite normal, 45 cycles, and then we take picture and process it. Now I can skip the multiplexing I just mentioned. So target 1 does not have specific probe. Target 2 has, and because target 2 has, its fluorescence shown here on Y scale is much higher than here, so they shift. So you get the peak of target 2 separated from target 1 quite nicely. If not, this will be overlapping. This is some detail how it looks like. This is sorry, oh, it works. Oh, good. Yeah. Yeah. So, oh yeah, here it's stuff. So we can also improve it, but we couldn't at that time because we didn't have dPCR, which allows us capture fluorescence image as function of temperature. So, but you can see here, this is chromosome 18 gene with EVA green only, the black one. This one is with chromosome 21 with EVA green only. So you see that the amplitudes at room temperature 25 here are very close to each other. But the moment you add FemPro, it jumps up, separates from 18. You can detect it. You can even improve it. In this case, if you did take picture at 90 centigrades, all EVA green-based fluorescence, which is linked to double-stranded DNA, will disappear because there is no double-stranded DNA anymore. You get only fluorescence from FemPro and no background, basically. So you get very precisely the FemPro here. And if you take even overlapping here, you know how many of FemPro you have there, which means 21. And so this total number minus 21 is 18. So you can do multiplexing of two genes using single color. And it's shown here basically when you add the FemPro, one band will basically split into two bands. Even though it's not very well visible here, but the moment you switch to histograms, it's quite nicely seen. Well, many times I was asked, so yeah, fine, fast PCR, because our fastest PCR was like 6 minutes for 40 cycles. So where is sample preparation? How long does it take? I don't like the question because I didn't do it. Because it's complicated. So PCR much easier and straightforward. But we decided we have to somehow move to it. So you see that sample collection in China from people's mouths, and we can go to classical system or complete system, which is a commercial system, the magnetic rod, and to move it here. So, and technically what you said before, step one is like dump it there, lysis, then binding to magnetic particles, keep magnetic particle, washing it, and then goes to PCR solution, and then you run it. Here is quite nicely seen. This you see the white spots here are basically end of all the sample collection stops. So you see how many is inside, because this is for the pooling technique, because expected answer was typically nothing in each tube, so there is no two individual samples. Okay. And so we decided to make the system finally, and but we have some project to be paid for it as well. So we have this PMMA chip. One is filled with fluorescence to improve contrast, and system which can process it. Chip is here, two types. Principle is described here. Oh, don't see anything here almost. So you pump sample with so take sample with lysis solution and magnetic particles, shake, wait for it some time, and pump it through the system. And here's magnet. So magnetic particle will be captured here. Then you move it here. There's oil. So you will remove all the debris you don't want to have, or most of it, and then move it to sample through PCR chamber, which has roughly 6 microliter volume. And you can heat and cool this thing while looking at it using fluorescence measurements technique. So this chip is made from PMMA. We prefer it. This one is PDMS, and we like it. It's not better. The reason is very simple. I can get quite a lot of them made by CNC, one side, and the bonding moved by ourselves. Very convenient. Okay, this is a description of the system, very important. This is a block diagram on the system. It's same thing as before. Basically, you have you control temperature and cycle it, and then you have the optical system here to detect fluorescence. This is a USB-based system to control it. You can also run automatically. And one thing I would like to mention, this is quite, I like it quite a lot. In 2010, we developed technique to measure temperature inside microfluidic systems. And it's very difficult to do it normally because how do you get like probe inside? Like this closed system. So there's a probe, you cannot get probe inside. If you get probe inside, you will influence the temperature anyway. You can use infrared thermometry, but with infrared thermometry from 8 to 40 micrometer wavelengths, the problem is you don't measure temperature, you measure power of radiation emitted from the system. And it's from the surface of the system, not what is inside. And we are interested in what is inside the microchannel, not what is on the surface. Also, you use like Stefan Boltzmann law, you know that the power of emitted fluorescent radiation is function of emissivity of the surface. So if some student goes there, put finger there, you will change reading of the system, and temperature will not change. So we didn't like it too much, and the resolution is kind of poor, many headache. And you can look through the glass because glass is not transparent for infrared radiation at the wavelength. So problem. So what we decided, because we were dealing with PCR all the times, so we use a PCR solution after PCR, after amplification, which contains EVA green or cyber green. Typically use EVA green, but it doesn't matter. And there is one thing, for instance, fluorescent. You can use fluorescent to measure temperature. Some people did it. Problem is fluorescent has one issue. It's called photo bleaching, and which means that you keep shining blue light on it. You will see that you will monitor green light coming out, and green light amplitude goes down. So you do calibration of the system, but after 10 minutes, calibration is completely off because amplitude drops to half. So we took DNA double-stranded DNA after PCR, ran melting cap analysis, and in melting cap analysis, I don't have a picture here. Amplitude also goes down of the light by photo bleaching, but location of the melting temperature never changes because that one is done by the DNA, nothing else. So yes, amplitude goes down, but you scan curve, you find out where is a melting temperature. This is always the same. And what we do is here, we have this our chamber, and we basically measured. We did many images at different temperature, and then calculated melting temperature at each point. And it tells you one thing. It tells you how to heat up the heater to get the melting temperature at each point. So from that, this is temperature distribution at the chip. And it's very precise. Single point measurement definitely is not. We can also do the double point because two different DNA is possible, but we typically are single point. So we know how much is changed. And on small TEC, we found the temperature non-uniform like 10 degrees, which was huge. So we have to fix it. The big TEC was okay, that was quite flat, but the small one, we had a lot of headache. Yeah, so this is what we do, how we measure temperature inside, and we use this technique routinely for microfluidics. And good thing here is that the fluid itself is a temperature sensor. So you measure temperature exactly where you are interested in, not somewhere else nearby. No, exactly that point you are interested in. You measure temperature there. We did for GPCR, qPCR, and some microfluidics. And here I have this is just cross section of the optics. I might go very quickly through because it's basically said before. So 3 filter system, 1, 2, 3. And LED for the lens here, focusing on the bottom, electronics and cable going to processor. Yeah, and this is tested in Czech Republic, north part of Moravia region, eastern part of Czech Republic, in biosafety level hazard 4. Even she is not operated the moment that mode, but this lab is equipped for biosafety hazard 4, which is the only one in Czech Republic we have. Military institute, and if it operates that mode, she would be like a complete scaphandler, completely closed, and there's even tube for breathing. There's a main pipeline on the top, and she would plug that tube into the pipeline, breathing that air. So completely separate environment. So this is equipped for it, and she was doing the testing there. but because we didn't manage that way, so she didn't have to do this. Okay, so some results again from SARS-CoV-2, and this is raw data here, and after extraction, because this was marker fitting and shown here, critical temperature 18.6. This is melting analysis, so blue is melting curve, and when you do minus df over dt, you get a peak, and 80.268 is vicinity to the temperature we expected. This is lamp, so this can skip. And as a dual system, what I showed before is single chip. This is dual chip. You can detect two samples at a time. And now we are moving to 812 colorimetric detection. There are different systems. Like one is based on photodiodes, photodiode and three LEDs. Another one is system of white light illumination and RGB sensor. And this is how it looks like for basic testing, and same thing here. So it's not very, it's quite messy, but we are looking for two-hole principles, so it's good enough. That's the results. And one thing is last slide, I would like to mention, if you run LAMP in vacuum system like this one, this is SolidWorks design, this is actual system made by CNC machining. You can pump chamber and measure pressure here, and then you can look at the use pulse modulation system, and you can see how duty cycle is changing with pressure. And I would like to mention one thing: there is some defect in the design, because this dropped far too little. It should drop to few percent, not to 45% or 65. Okay, but this is just matter of fixing the design. So yeah, so I would like to acknowledge my collaborators. There's plenty of those because I'm working in the system for 20 years, and yeah, different agency funded our work, and thank you for your attention. That's all any questions. So
thank you for the presentation. Do you have any questions?
Where is this photo taken?
excuse me?
Where is this photo taken?
Yeah, Binjinding. Binjinding is highest part of Eastern Chile Mountains, which is south of Xi'an, city of Xi'an. It's a small place, 10.5 million people only, and it's about 40 kilometers from my home, and takes you can drive to 1500 meter altitude, and it's 3015 meters. So you have to climb up or walk up or climb up. It's not climbing; it's like walking into steep hill, about 1500 meters up. So I was like I would say 8 to 10 times. The highest point there on Eastern Jinling. Jinling highest point is Taibaishan, which is 3,720 meters. But unfortunately, there is view to some facility, probably, which is listed on the Wikipedia, so it's not that secret. And last sentence in Wikipedia on that page about Jinling Mountains is believed that China store nuclear warheads in Jinling Mountains. And at 3,400 meters is sign no foreigners beyond this point, and police kicked me out twice. So yeah, it's the highest mountain there, 3.7 thousand meters, but this one is 3,050 meters. And this one is somehow not recommended to go, but I went there many times.
My question.
Yes.
Thanks for the presentation. I've got one question about the reagents that are needed for all the PCR measurements. So you've been talking about sample pretreatment inside the device before doing the PCR, but I guess that there are other reagents that are required for the PCR that should be integrated within the device. So do you have, apart from the temperature cycling that is needed, is there any other reagents that should be integrated within the device after doing the sample pretreatment outside?
I'm not sure if I got your question, because first of all, please be louder a little bit. And second thing, so you said what should be integrated together?
Some reagents that are required for the PCR
Sure.
should be integrated within the device, I guess.
Yeah, we did think about it before. We didn't do it yet. What would be quite nice to have lyophilized solution. So basically you have lyophilized everything except, and you send in sample with correct volume. So when you dissolve the lyophilized solution, you get correct solution. We plan to do like this, but never done it. Just talk about it. We are in talking stage, unfortunately, so far. Okay. But you're right, definitely. Yeah.
Thank you very much for the presentation. In the case of the digital PCR, you use only a single sample, let's say, silicon sample?
Chip.
Chip?
Yeah.
You put the solution, how do you get, or how do you include the control?
Typically we plan to do it for two different genes. So they are sort of, we are not interested in absolute copy number. We are interested in a ratio of those genes. So from this point of view, I'm not sure if I'm answering your question, but we are more interested in this one because when we talk about two doctors about absolute quantification, I got very funny answers always. Like, when do you need it? What do you need it for? Like, oh, it's good to have for HIV. So what for? So, oh, because you can look if the treatment is working. But sorry, with qPCR you can also see it. So why do you need this? Like much more fancy. But the moment when you absolutely need it is like looking for the like trisomy 21, trisomy 18, these things, because there is ratio of two genes. Or there might be some cases when you are looking at a ratio of something with respect to GAPDH, for instance, like housekeeping gene. But sorry to say, I like the technique, but yeah, the like usage or utilization seems to be a little bit like oversold. But for that ratio 21:18 is clear. You cannot do this because you know it. For qPCR, if you change critical threshold by 1, it means 100% change. It was twice more or twice less. And absolutely no way you can do 10% changes. It's like, yeah, I can see some company are claiming that possible, but this is just a joke. Okay, so it's a category of like that are doing funny. But realistically, you cannot. But dPCR can do it. So that moment where you need to know precise ratio between two genes, the dPCR makes sense. And one is like, and you're looking only at the ratio. So absolute quantification doesn't matter so much, but does matter how much and more is one of them. So,
And when using the smartphone?
yeah, it can be louder to the eyes of heart. Sorry, I lose my hearing. Okay.
When you were using the smartphone as detector?
Yeah.
In this case, you were analyzing the image?
Yeah.
You were doing an image analysis or just measuring the current?
No. It's image analysis. I can show it to you here quickly. Where is the image? We have MATLAB script, which does it, and does few things. We started with doing it on this system. Actually, very convenient. We have this in our lab. We switch from very expensive, very poor special camera for microscope into Canon camera, which we found is much better because I use R6. It has 45 million pixels, and sensitivity is also pretty good. So you like it much better. Okay, so we process the image from here. And there is somewhere description how it's done. There's some calibration, and we detect the location of the chip based on some functions and empty spots and so on. And also here correction for non-uniformity imaging. We fill it by fluorescein, which is uniform, of course, but we look at non-uniformity of the image, and we have map from it, and we apply map on the actual image to like make it flat, basically. Yeah, so we have this. And one thing which is I would like to also, yeah, this is uniformity correction for imaging. And one thing which you can say is there is no much science. I would say it's true, but I still like it. It is one here, and this one. We created opposite system. We have MATLAB. We can take layout of the chip, say what kind of distribution of negative, positive, or gene 1, gene 2, gene 3, what temperature, and we generate the image. And then we use it for new chip to learn how to process it far before we have the chip made. Because we submit that image to the second MATLAB script I just show you with the correct layout information, and it can start learning how to do it. So I don't have to wait for guys to make it in fabs and fill it with solutions, and for a couple of months struggling how to make it work. So you have this opposite. Yes, it doesn't matter, but I have some other sequence here. Yeah, so this is generated by MATLAB, and then using gene which we describe in MATLAB, and then process it. You get those data from processing here. And we also took this is actual image. This one. No, this is also. But we also look at somebody else's work. Like this is Professor Mu Ying from eastern part of China, the D chip. Made from PDMS. We created layout of that chip. So I would say one afternoon I was bored, so I made layout of that chip. We never made a chip, by the way. We only use layout, and we created image, how image with certain parameters would look like of this, and then process it. And we want to see the same parameters after processing. So that's why it's quite nice, because you know that both ways are working.
Any other question? We are almost like one. So just a very short thing, I have a doubt. How do you manage to confine the sample? Because I understand in this matrix of 4 hitters, you add a sample, positive, a negative. How do you manage to confine the sample just in the area you want to mix the samples?
The student printed a piece of paper, black circle with 4 dots. And he puts it underneath the glass, and he pipetted on those dots.
Okay, so you managed to not mix the samples. Great. So just to remind you, I think you wanted to speak about the Napolito toolbox. Maybe you can tell us a bit more about that. And
sure.
With this, we finish because it's a bit late now. And if you want to contact with Professor Neuschel, he will be here the next hour. We will go for dinner, for lunch. So maybe after he will still be here.
Thank you very much for reminding. There is like most of you here, they are doing some layout of chips. It can be integrated circuits, can be microfluidics like Stella does gas sensors, can be MEMS, can be anything. And if you deal with integrated circuits only, but take a big word, so word, but call it only. But anyway, if you deal with integrated circuits, typically you don't need anything fancy. For integrated circuit, you typically have rectangles. If you want to have anything else than rectangle, like in Edit, for instance, software, you can do pie, you can do circle, you can do donut, and I think that's about it. And polygon. We can also do one thing. We have done it before in Cadence. We showed the layout editor a long time ago. We wanted to get spiral. And what I have done, we wrote the equation into Excel sheet, pull it down, got spiral data, then do some plus minus something, whatever, and I got eventually location of like coordinates of the spiral outside and inside. I created some cell called CIF, called Caltech intermediate form, which is description of the layout in text form. GDS, which people normally use, is binary. Okay, and then I was able to load this CIF into Cadence, but it was pain on neck and very complicated. I think I just showed it, but it doesn't matter. Very complicated, and problem is, if you want to change anything, you have to do it again, and not good, and very complicated stuff. So my former student, currently big boss in a center for CNST, some fabrication at NIST, National Institute of Science, Standard Technologies in Gaithersburg, in Maryland, USA. He is head of that of big team there, and he like 10, 12 years ago told me that he doesn't want to spend time with layout, that he wants to spend time with science. So it's layout, no science. Just spend plenty of hours spend with it, and you can publish anything. You can go and you can publish layout. Nobody cares about layout, the publishing, so publication. So you have to have the results, and then you can publish results based on your layout. So he said we should shift the time from utilization more from layout to science. So he came out with software called Nanolithography Toolbox. And Nanolithography Toolbox is very new version of it's not layout editor, it's layout generator. Okay, editor is wrong word here. And you can see this is a classical layout of I think oscillator, I believe, CMOS. This one is my bolometer. This one is our microfluidic cell for temperature measurement. And these two on the bottom are created here, not by any editor. In NT software, he used Bezier function, I believe, to smooth it. So in normal, what they do is in 10 nanometers, they do a lot of e-beam lithography. It doesn't matter, the principle is the same. So you can get either classical like broken line, and if you look at the high details, it's not very nice. In this, you get smooth lines. Let's skip this part, not important. Yeah, this is the thing. And now it's just structure of the software. So you can use graphic user interface, which is not terribly useful, but you can do scripting. Scripting we use all the times. And also, you don't have stepper here, I believe, but they have stepper. And when they make reticle, this mask for stepper, they have to have some data on the frame of the reticle to be recognized. And they have in the database, you can load it in directly in the software. Okay, machine resources. And for EBL, anatomy lithography, also there are some corrections you have to use. So here is graphic user interface. You can open it and choose whatever is available, and then some parameters that you can get it. You can get, for instance, like this is sinus with some attenuation with certain width. And how you get it? You put the numbers here and say create GDS. It pops up. Okay. And as I said, this is not very useful. It's okay, but the other part, scripting, is much better. Because you have to redefine few structures and you end up with GDS over structure, not complex GDS. Okay. This one is non-structure. It's shown this layout here. It's shown is described here. Basically, you can look at it. This NT software is like a set of parameterized blocks. There are two parameterized blocks. One is here, one is here. And this one is 4 times once. So that central one called circular string. Here are parameter for the circular string. And this here is called conradial V2, and there are parameters for it. So there are 4 of them. You see there is location of the origin, the first two, and here is angle of rotation. You can simplify it, have only 3 lines, not so many, by using something called polar array. In polar array, you would say this is cell, and you want to step it 4 times with the degree in between. So last about 12 years, I would say we don't use any except as a viewer. I use edit quite often, but to see it, not to use it. And last 12 years, I use do layout only here. Okay, like this. And for instance, there's one here called Bezier function, and it's actually quite easy to make it, even looks so fancy. You know what you do? You type it in Excel. You type this coordinates, this guiding point, this coordinates, and then do the same thing here for second one, and then in Excel just shift everything down. You will generate the numbers up to here. Control C, Control V to the text editor here, and you have this done. And this is one cell. This is flipped, mirrored this cell, and you can do the polar array to get everything here. This structure is different. This is like entire cell is this block here. Okay. And this is not interesting. Yeah, you see there are also fractals, and there's plenty of those structures. By the way, this picture here, like nothing is made classical way, everything is made by the software. You see the structures there. So fractals, and there's also some like for physics, you know, that classes they talk to each other, affect each other. So you can have like this ring next to light guide, and yeah, not physical measurement. You know much about it, but yeah, plenty of other structures are available, and including structures for microfluidics, which are interesting for me. Yeah, this is our PCR. The one is done. And this is very quick, and I will show you some examples for layout editing. I have it here. This yes, is some picture from there. But what happened? I asked my students that I don't care what they design, but each of them will design some microfluidic structure. So we created some blocks. This is copy of Agilent chip for electrophoresis, and quite precise because we had it under microscope. I would not call it reverse engineering, we got inspired, okay, by that which we copied. Okay, so we copy it as it was, and this is 6 line of codes. This is structure. Another sound is for rotation, similar as people did in not Karlsruhe, Freiburg. They have some droplet generator which looks like this. We copied from them. This is generator of gradient here. This is CE chip. Yeah, but the one is from Hong Kong. Show some details. Not from Hong Kong, for Hong Kong, what did you say? Because we did the design, they did the testing. Yeah. So there are those chips you just saw. We fabricated them, and this is some chamber for cell measurement, CE. This is a separator, and it's a generator of droplet. This is nothing. It's just he like it. So students, so he made this chip, and this is separator. This is a Hong Kong chip, and yeah. So this is what I mentioned before to you. We do quite often that we measure temperature, and we measure temperature by measurement by melting analysis. So we scan this. This is also from this layout, and we calculated melting temperature, melting point, which location it is, and we know what temperature is at that point. This is this one. And from that, we use different flow rate, and we calculated heat transfer between the walls and the solution, because that point start moving with flow rate. Okay. Yeah, this is gradient generator. So more concentrated, less concentrated fluorescein, and the location 1, 2, 3, 1, 2, 3, and third one is here, which is this point to get gradient of fluorescein. This thing, and I'd like to show you one thing here. I'll edit, open it. There's some examples like a 3D testing. This is a microfluidic chip I mentioned before. Oh. Hey, how come this is so funny? Yeah, here. Yeah, so it was, of course, nightmare for the lady who was cutting it by dicing saw. She asked me, so can I go with the dicing saw through this? I said, no, please don't. So cut it here away, mount it, cut it here, mount it, and yeah, so she was not very happy. So I had to buy that chocolate to calm her down, because yeah, this is a very stupid design for dicing, but we wanted to have like demonstration for the devices. And here, this chips. Hong Kong might be good. Yeah, this is chip from Hong Kong. I mentioned before. The design is quite nice. Yeah, so this is double spiral, and after etching, it's calorimeter, because there's temperature. There is one is sensor, one is heater, and you can do scanning. What is it? The differential scanning calorimetry. Yeah. So one tube is here, one tube is here. Quite. The design was quite time consuming, but you can see it's quite decent way done. And I hope I have bolometer here somewhere. Research chamber. Maybe here a second. Sorry. Maybe here somewhere. Okay, later. So this is array of bolometers. There is 100 bolometers here next to each other and 10 for reference. And if you look at the detail, the bolometer is here. And what is interesting, I would say, is here. This is another toolbox, okay? The software. And it has 490 pages, which means every single block is described quite nicely. And there is what is interesting was NIST. This is very special organization one way, that they don't allow anybody publish anything without having it approved. And the approval process is absolutely pain on neck. And but when it's approved, it's almost impossible that there's mistake. So here, took them forever to release it, because they wanted to make sure that everything is so perfect, so they don't like damage their name. And very well described. So this is I want to show some blocks here. Control F. So if you want to make, for instance, bolometer, it was done for us, and it's seen here, and there are some parameters. The parameters are here. So I want to create this. What I do, I call the bolometer L, and I just write the numbers. And when I have it, I get this layout. Okay, so making life so simple. You can see it here. Basically, I have it the same structure here, because I didn't use all layers, because some of them I didn't need it, but it's here. And also, I mentioned before, where's my, like here are Bezier curves. But we use only Bezier curves now. Normally for the metals in chips use this exact line. We just don't like it. Maybe like this better. And making this is so simple, so why not? And so I took this 1, 2, 3, 4 points into Excel sheet, second one, and then extended, and I got all 10. And copy it from Excel to do this time. And I showed it before, I don't want to take much of your time, but this is, we use software called Atom as a text editor. And why? Because Rob, who designed the entire system, he did customization of the software. So it knows that if there is CNST extension, it knows what those codes mean and changes color. So very convenient to work with it. And this is structure of I mentioned before all that com drive MEMS. And if you want to, you are happy with this, you want to make it Control-1, and it generated GDS of the structure. And now what we can do, we can open it in KLL or edit and to have a look. I can show it to you. That's the last thing I do. Don't want to take your time anymore. And you go here, I'll edit, file, import mask data, GDS. I go here, actually the same one as before, import. Yeah. So total structure here. Okay. You want to change something, you go to text file and change it. You go like -50, just for fun. Save. Of course, it doesn't make any sense. Sure, but I'll just show it to file, open. Should be the same one. Where are we? No, I don't open it. I can say file, import. GDS, I want to check if this is one. Browse. MEMS GDS. Yeah, I have Chinese time, so -7. So it's a 129, 28. So open. Import. Okay, fine. I can open twice. No. File, import, GDS, import. See, and of course, I know it will be nonsense, so I just messed it up because I shifted. Okay, so you can see just you change the number, Control-1, and generate new one. So I sometimes combine both because it's convenient in LED to look at some locations. So I move it to the correct location, check all these locations, and I put it into the text files sometimes because I'm lazy to think too much. Yeah, but it's very convenient. Okay.
Thank
Sorry
you,
for the time.
Pavel. Thank you for sharing all this information. Gracias, Abela. Hemos
Nada.
extendido un poco.
Bueno, si la gente se queda, ya está.
Está bien.
Bien.